Okay, so we're just showing a quick probability tree. What's a probability tree of rolling a coin or tossing a coin twice? So without the probabilities, that's how you did a tree of how many different ways. But now calling it a probability tree, putting these probabilities down. So let's do this like real quick and mirror what the next things are going to be. What's the probability of rolling heads and then boom, heads? Now, from yesterday or the last 2 days of notes, whichever it may be, what is that upside down U called? An and or an or? Three, two, one, go. It's an and. And what does that mean? Well, it means two things. First of all, it means multiply. But the second thing means I'm rolling two coins. What do I keep saying rolling? Flipping two coins. I'm flipping a coin and then I'm flipping the coin again. So what's the probability of getting heads and then heads? It's this probability. Probability of getting heads and then picking up that coin again and rolling heads again. So it's half on the first try and half on the second try. But to say specifically what's the probability if I get heads and then heads again, that's why that gets a little bit lower. Like, what's the probability I flipped a coin 8 times and I got heads every single time? We know that's not likely to occur. So that is 1/2 times 1/2 times 1/2 times 1/2. That's 4 of them. 1/2, 1/2, 1/2, 1/2, all the way multiplied. 1 divided by 2 to the 8th power, which I think is 60. No, 2 to the 6. 2 times 2 is 4. Nobody cares about this. 2 times 8, 16, 32. 64, 128, 1 out of 256 chance, which is a very low possibility of getting 8 heads in a row. You know what's funny? What's the probability of getting, let's see if you can answer this in 3, 2, 1 seconds. What's the probability of flipping a coin and getting heads? And then flipping the coin and getting tails on the second one specifically. 3, 2, 1, go. It's the same. It's a 4. All right? Because it's a 1/2 chance and then a 1/2 chance. Because I'm being specific, about what happens on the first and the second. So anyway, flowing along a probability tree is another point to make. I wonder if I can just go back. Nope, that was my writing there. Go forward. Well, I'm going to try to erase this, but it's going to erase probably the whole tree. Nope, success. Yay, success. Okay, one more thing. What do those two add up to become? 3, 2, 1, go. 1. What do these add up to become? 3, 2, 1, go. 1. What do these add up to become? 3, 2, 1, 1. Okay, so each little separate tree set of branches, when they account for all the possibilities, each one of these add up to 1. So when we go to our notes, I wish I could do this question maybe tomorrow. I don't know why I put that there, but it is kind of like something I made up about my Lockport ware that I use. That's what this scenario is. And don't equate D, E, and F to be the same thing in each one of these. Okay, I think I'm in a good spot where I'm not in the way of this tree. But that's the same thing where I have maybe a 3-sided dice. I don't know, that doesn't really work here because these probabilities are a little bit off. But in the first thing, either A, B, or C occurs. And then after that, D, E, and F occurs. So how does this all work out? Well, the first thing is we're being kind of cryptic. We're getting you to exercise. What should those 3 yellow things add up to become? 3, 2, 1, go. 1. Okay, so either A or B or C are going to occur. There are no other things that would happen first, according to this probability tree. So to find X, Y, and Z, in this case, this is Y, we got to solve. It's hard for me to write when it's this small, 1/4 and 2/5, so I got to write that over again. We're making you solve for the beginning variables just to exercise the idea that in each one of these cases, each one of the groups of trees, either A, B, or C are to occur. That's 100% of the possibilities. So that's how I find Y. And then just for grade school, multiply by 5. Okay, that was 5 times with the pen. and multiply by 4. I'm teaching the students how to get a common denominator when you're adding fractions. Goodness gracious. Pen is actually awful today. And then I'm not formally going to solve by undue operations. I'm just going to figure it out. By the way, 20 over 20 is equal to 1. So what does y have to be? Looks like I'm missing 13/20. No, it looks like I have 13/20. My bad. So y equals 7/20. That makes up the 20/20. Very simple once I get a common denominator. And I'm going to go to this tree and put that 7/20 then. And leave it as a fraction for right now. And then finding x and y, I'm gonna get rid of x and z. Sorry, same thing. In that little thing, after a occurs, either d, e, or f will occur. So these are the only 3 scenarios after a occurring. So those should add up to 100 as well. So it's 0.3, 0.4, 0.23, 0.4. So 0.23 plus 0.4 plus, was that x? Sorry. X, yeah. Didn't know where my x's and z's were. And that should equal 1 because either that, or that will happen after a. No other possibilities. That's 0.637893, 0.37. Is that what's left over? Yes. Right? Yes. Anyone? Verify with their mental math. Just make sure my mental math is on spot. And then I'm going to erase these highlightings after because I'm going to use them for a different scenario. After C occurs, either D, E, or F will occur in these scenarios after C. So therefore, those should add up to 100. So Z, stay red, plus, 0.48, 0.35. And that should equal 1. 7883, so Z equals 17.17. And then I'll go ahead and write that down because then we can answer the next parts. All right, and we do have one brand new thing on here, but that's not the start. So, and we're going to happily cross off letter 6, or number 6, sorry. Okay, so now what's the probability of A intersect D, which we should know is from yesterday, and I actually asked you today on a verbally tell me 3, 2, 1. Is this an and or an or? And you said and. This is an and. So what's the probability of A then D? So this is probability of A and then D, which means multiply or add. 3, 2, 1, go. Multiply. Because really what this means on the probability tree is, what's the probability that A happens, and then after A happens, D happens. So it's moving along that probability branches just like I did with the flipping of the coins. That's why I wanted to go over that, so you understood that concept. So this one's pretty simple. And you feel free if you want to get your calculator out. I am not touching these buttons because I shouldn't have to be the person that shows you how to type out your calculator, press enter. It's grade school. Okay? All right, so I'm going to erase you don't have this choice to erase your highlighting. Or maybe you could try to kind of use different colors for the next one. This one's kind of crazy. So I'm going to highlight for 2. I'm going to highlight for 3. I'm not for 4. And then 5, I have to give you a different definition of what that means, or a new definition, not different. Okay, so here's what's strange about probability of E happening, and that's all that they ask you. Okay, so I'll take this out specifically. I'll only use one color. But here's the problem. When they say, what's the probability of E occurring? E could either happen here, or here, or here. That one that I had to find. So those just can't happen, though. How do I get to that first E? A happens, and then E. Or B happens, and then E. Or C happens, and then E. So that's how I'm going to have to write this right here. The probability of E happening could happen in 3 different ways. A and then E. Or, nope, sorry, reverse that. Gives the students time to catch up with my writing anyway. B and then E. And I printed this for you. A, it is Wednesday shortened, but B, also that tree thing. You could have put that in your notes, I guess. This would, really didn't have to be printed, but that's fine. Oh, we have two word problems, so that is good. Or C and then E. So that's how E could happen in three different ways. That's what you really have to figure out on this when you have questions like that. So what's the probability of A and then E? 1/4 times 0.4 plus or B and then E 7/20 times 0.56 or that's the word or again, sorry, made it worse with that little line there, or C and then E 2/5 times 0.17. Press enter, type it in as your calculator. If you don't know where the fraction button is, then do 1 divided by 4 in parentheses, then times that 0.4. Should not have to teach you how to type that on the calculator. And if you don't type that on the calculator correctly, you're wrong. All right, and that's what we should be able to figure out there. Okay, now the next two are a little bit weird how you do this one, and I'll explain why we could simply just do one little thing here. Remember, I'm going to erase all my highlighting to highlight the next one. Kind of said I wasn't going to highlight it, but I do like playing with the highlighter there. So first of all, as a notational thing, you need to remember that this means the probability of not C occurring, which actually means the probability of A or B occurring. And I know you might end up trying to overdo this one, and you really shouldn't. Because, so one way we could do this is, okay, let's look at the probability of C. And if you ultimately understand this question, then this is, quite frankly, 1 minus C occurring. It's the complement. But wait, Mr. Samuels, why wouldn't you continue to do the other trees? Because that is equal to, and believe it or not, it will equal to 1/4 plus 7/20. All of these end up equaling 3/5. But why didn't you do this, Mr. Samuels? Why didn't you say, okay, the probability of A occurring could be A and then D, or A and then E, or A and then F, and then add that to the probability of B and then D, and then B and then E, I'm sorry, or B and then F. Again, what do these all add up to become? 3, 2, 1, go. 1. What do these all end up to become? 3, 2, 1, go. 1. So ultimately, you will just have 1/4 when you're done. All right, and that's what's really going on there. So that's why I just did 1/4 plus 7/20. Because A occurring could be A and then D, or A and then E, then A or then F. That will be 1/4 when you're done. 1/4 times 0.23. This will ultimately end up being 1 times 1/4, making it in simplistic format. Fumble. Okay. All right, now put a big star by this. This is actually called dependent scenarios. I know in our stats class, we really break these down. So if you end up in your 4th year here, definitely be a big probability concept. Not a big deal. We're not going to go too far on this one. But I do want you to write down, what does this bar mean? All right. And this means the probability that E occurs, and then that line, maybe I should highlight it. Given that A occurs. So it's already saying that A occurred. So what's the probability of E occurs given that A occurs? It's assuming something has already happened. So when I go to my tree up here, And I gotta go ahead and erase these. All right, don't want to erase any of my givens or things that I found. There we go. Oh yeah, I don't want that circle anymore. We're assuming this has already happened. Darn it. Okay, I don't need that circled anyway. So, given that A has already occurred, what's the probability E occurs? So we've already assumed that that has occurred. That branch is dead now. We're just specifically going to that E. And if we assume that A has already occurred, then the probability of E occurring is 0.4. The flat out percent of E occurring after that branch is assumed. Right? And that's how probability in this kind of scenario works. Now, I showed something different with first hour. I think I'm going to leave it at that. I'm going to leave this as maybe our new concept for the day, what this means. Write that down, what that bar means. And it assumes this branch is already existing, so you don't incorporate it into your answer at all. Okay, because it's assumed, and that's what dependent probability actually means. This is depending upon A occurring. What's the probability of E occurring? Okay, now, specific to this, there is a relation here. All right? I'm going to tell my story. Oh, hopefully my sister doesn't watch my YouTube teaching videos. Because there is a little pet peeve of mine that I have with my sister that just showed itself up in over Christmas break, which we had a great holiday with my sister, their family, and my family, and my mom, and all that other stuff. Good stuff. My my wife's parents, which are in-laws, were also there. But we got picked up from the airport, and they have a 4-year-old granddaughter, and the daughter's also there, so the mom. And that 4-year-old is climbing around the van like a monkey, not strapped in. No rules in the family about wearing seatbelts in the car, which drives me absolutely nuts. Drives me crazy. First of all, she's a 4-year-old, so she's bothering everybody, but not being strapped in. And you know why? Back in the day when my sister was parents of their 1, 2, 3, 4-year-olds, they never made them wear seatbelts. Could not stand it. Did not understand it. My kids know. Don't even have to say a word. They all strap in because they know the importance and the statistics of how it's safer to be strapped in the car, so on and so forth. So when I read this question, this is true. When parents do it, then more than likely the students will. When the parents don't, more than likely the ingrained behavior is the students will not. So that's what this statement kind of says here, the statistics. Study reports that 68% of adults wear a seatbelt while driving. Stop! What percent don't wear a seatbelt then? 3, 2, 1, go. 32 is very simple, and you have to incorporate this in here. All right, high school student also in the car wears a seatbelt 66% of the time when the adult wears a seatbelt. I would have thought that would have been higher. And 26% of the time when the adult does not wear a seatbelt. That's what I mean. You're more likely to wear a seatbelt if your adults ingrained it in your behavior. So here's what's got to happen. Let's read the last statement and show how this pertains to a probability tree that we have to put up here. What is the probability that you select a high school student and they're wearing a seatbelt? Well, wait a minute. You could be in one of two families. You could be in a family that the parent wears one or they do not wear one. So we got some possibilities going on here. So here's the tree. The first one's the parent. The second one is the child or the student, because we have two different people we're comparing in each set of these trees. So what's the probability? And the whole thing is wearing a seatbelt. So I guess I could put that along the lines. I'll do this a little different than the other hour. Wear, and then I'll just caveman it, not wear. And we're talking about seatbelts. And you already said it. There's a 68% chance. I think I reversed this. We put the name here and then the probability on the bar. But either or, it doesn't really matter. But it says right off the bat, adults slash parents, 68% of the time they wear seatbelts when they took a survey. Well, that means not listed in this. The only other option is 32% that they don't. This is the whole idea that these should add up to 100% of the possibilities. Okay. Then the students. Well, here's why we have to have two trees here. You could be from a family that ingrains it in your head, or from a family that does not. My family is the top. My sister's family is the bottom. Bam. Okay, so if you were in a family that wears a seatbelt, or the parents, then it states that the student is 66% likely to be wearing a seatbelt as well. That means what's the percent that they're not wearing it from this family? Three, two, one, go. 0.34. So not written in the question. We got to get this, labeled here. Where, and then not where. I think I'm just going to shorthand it to where, not where. W, non W. And then if you're from the family that isn't, it does not normally do it from the parents, I mean, then you're more than likely not to do it and not be told to do it. So that's 26, and then you get the drill. This is 70, 90, 74. Hopefully I put that right there. I guess we didn't use it because of this. Okay, and then again, where, not where. Okay, then notice how this is worded. What is the probability that a randomly selected high school student wears a seatbelt? Well, you could be from a family that ingrains it in your head, so your parents wear it, and then you wear it. Or you could be from a family that does not put it in your head, but you still wear it. Right? So what this is the probability of the adult wearing it and then the student wearing it, or you could be from a family that an adult doesn't wear it. ANW. My N looks like a W. Let me rewrite those letters. Adult not wear it. I wonder what I wrote last year. I wonder if I wrote the full words. But you still wear it. So the student wears it. So NW means not wear. So you could be from an adult that does wear it, therefore you do wear it, or you could be from an adult that doesn't wear it, but you still decide to wear it. All right? So exercising the idea that this is multiply, whereas this is add, because it's this scenario or that scenario, depending on how this works. And that's how a probability tree works in these kind of questions, which are kind of common when we talk about statistics scenarios. So 68% chance the adult wears it, and then a 66% chance that the student wears it, or 32% chance that the adult doesn't wear it, 26% chance that you still wear it even though your adult doesn't. And then I shouldn't have to be here to how to calculate that on a calculator. Very simple to plug that in and press enter. Just checking my time real quick, 11:08 on our randomly Wednesday days. This is our second Wednesday? Right. We're in the second week already? All right, we're plugging along, man. We're almost done with January. I can't wait till we're done with February. Getting into the spring. After Valentine's Day stickers, then I get into St. Patrick's Day stickers. I love St. Patrick's Day. It's like my spring. It's like, here's spring. St. Patrick's Day is a big checkpoint. Then a week after St. Patrick's Day, it's spring break, right, everyone? Right. We got to think about these days as we move through the stretch in the calendar. By the way, this is our biggest stretch in the calendar. This is day 2 of 24 days straight without a day off. Just so you know. All right. Everyone good? Okie dokie. Same old, same old. Oh, this reminds me of the Common Core days that really destroyed my mind as a teacher and as a parent. Remember, I got a junior and a freshman. You guys are sophomores. Oh, when my kids were in that Common Core movement, I was buying scratchers every day as my retirement policy of getting out of teaching because it really drove me nuts, the whole movement and all the big changes in math. By the way, what's 2 plus 2? 4. Did that ever change? Then why did we change math? Anyway, let's move on. Ayanna loves to play scratch-off lottery tickets, and she plays every day. Woof, wow. She plays the holiday-specific scratch-off 73% of the time. Now, she's really stupid, because watch this next part. She wins 87% of the time when she plays the holiday scratch off, but only 35% of the time when she doesn't play the holiday scratch off. Why is Ayanna stupid? What should she always play? The holiday scratch off. You win 87% of the time. Why even go into the other ones? I don't know. I don't get it. Maybe the payouts are way smaller and you don't get as much as reward. More risk, more reward. Maybe that's what it is. Don't be so mean, Mr. Samuelus. So look at what it says at the top, but only. Oh, here we go. What is the probability that she wins on a selected day? Well, here's the two scenarios. It's really holiday ticket or not. What? I just changed an H and an O into one letter. Holiday ticket. And then I guess I could take each branch and say, I'm going to reverse it. Win. Oh, no. Holiday ticket, yes or no? I'll play the holiday ticket or I won't play the holiday ticket. I guess that's the best way that we could say that. And then I don't really care how you label it. It's all about getting the correct percentages. So whatever. It doesn't matter. So she plays a holiday scratch off 73% of the time. Now I'm going to put the probabilities on the branch itself. Switch it around and you do whatever you want to do. What is the percent that she doesn't then? 3, 2, 1, go. 0.27. So in the word problem, it's not written. You got to understand that these should add up to 100%. She either does or she doesn't play that ticket. And then here's the next thing. Win or lose. And that's what we end up writing on our second branch. So it's a little different labeling than the last one. Okay, and then she wins 87% of the time when she plays the holiday. All right, I don't have to keep bothering with these questions. That means she loses only 13% of the time. But when she doesn't play a holiday ticket, she wins 34% of the time. So other tickets, she wins only 34%. That means 66. Okay, then same old, same old. So again, it's getting this labeled correctly with your percentages lined up. Understanding each set of branches add up to 100, and they should make sense now. Okay, what is the probability that Ayanna wins on a randomly selected day? Yet again, two things could have occurred. She could have played a holiday and won, or she could have played a non-holiday and then also won. That's why this is, a big-time probability that we have to figure out here. So how do I label that? Probability of playing a holiday and winning, or, and I could put union there, but I really want to write the word there, or, because it's this or that could occur. So these are separated by plus. Or you could play not a holiday and still won, right? And then it's the same old like the last one. You had a 73% chance of picking a holiday and then winning, or not holiday and then winning. So that's why this sets up those scenarios. Boy, statistics are huge, and probabilities like this, boy, when you watch a football game, that's all they talk about is stats. And things like this occur. They say this all the time. Monday Night Football, the record in Monday Night Football. So what's the probability that you break a record? Well, there's a probability you're playing Monday night and then breaking a record. That's kind of like a conditional scenario. You can type it on your calculator and then look at what it says next. What is the probability that she does not win? Guess what? It's just 1 minus whatever the answer to A was, because that's just the complement. These should add up. You either win or you don't win, and that's 100% of the possibilities. So that's why it's 1 minus whatever you get for the answer for A. So let me erase that. That A got all junked up there. Whatever the answer to this is. Okay, good. First video of the year. How do I even stop it? I don't even know. Here we go.